part 4 of our lecture. Alright, we're still talking about this idea of geostrophic balance, or geostrophic winds, which are an approximation to what the real wind is doing, where we're saying as long as we're away from the surface of the Earth, where friction is not so important, and we're away from the surface of the Earth and we don't have to worry about friction, and we're talking about horizontal winds, so we don't need to worry about gravity, and we're talking about things that are not like twirling, so we don't need to worry about the centrifugal force. We only have pressure gradient force and friction, and pressure gradient force and Coriolis force still to worry about. Great example of the kind of phenomena that have cyclostrophic winds are cyclones and anticyclones aloft. Here, I've drawn two. A cyclone over here in the west, it's an area of low pressure that spans an area of several states, and an anticyclone over here in the east, an area of high pressure that spans several states. Those lines that are around it are supposed to be isobars. So the pressure is lower in the cyclone and it's higher in the anticyclone. And if we have that, all we need is these isobars to get a visual idea of what the geostrophic wind should look like. In fact, I picked 8 places on this map to illustrate what the forces look like and how the wind is working on this map. Any one of these places you can take a look at on your handout or whatever and see how the air parcel is experiencing two forces that are equal and opposite. One is the pressure gradient force pushing in towards the cyclone or away from the anticyclone. Either way, pushing away from high pressure towards low pressure. And then in every case on the way there, we have a centrifugal force, a Coriolis force, which is equal and opposite to that pressure gradient force, always drawn in green. And then in order to get that Coriolis force, we need a wind. And that wind is then pointed in such a way so that the Coriolis force is 90 degrees to the right of the motion. Okay? And you end up with winds that are parallel to the contours, with lower pressure to their left and higher pressure to their right. That's geostrophic approximation. And this looks pretty straightforward. It makes winds that are basically going around the area of low pressure in a counterclockwise manner in the northern hemisphere anyway. It'd be the opposite in the southern hemisphere, but we don't care about the southern hemisphere right now. And around the anticyclone, you can see that the winds are going clockwise around it. Cool. Oh, yeah, there's some rotation, but honestly, these wind speeds are only a few miles per hour. If it would take, this cyclone is the size of many states. At these wind speeds, it would take days and days and days for that air parcel to make it all the way around. We can safely say that the centrifugal force is much smaller, and we don't need to rule it out. So we have this nice rotation in a counterclockwise manner around the cyclone. We have this nice rotation in a clockwise manner around the anticyclone. It's very beautiful, very straightforward thing to think about. Cyclones, like what we have there in the west, when they are aloft, away from the surface of the Earth, so we didn't have to worry about friction, they are big areas of low pressure with winds that rotate counterclockwise around them in the northern hemisphere. And the anticyclone, like what we have there in the east, is a very large area of high pressure with winds that rotate around it in a clockwise manner, at least in the northern hemisphere. Pretty slick. Notice too, in those slides I had the isobars evenly spaced everywhere just to keep things simpler. But they wouldn't have to be. Like here I adjusted it so that like some of the isobars are farther apart, like the ones in the western United States. But then between the center of the cyclone and the center of the anticyclone, I have the contours closer together. Therefore there's a stronger pressure gradient force. Therefore there's a stronger Coriolis force. And in order to get that stronger Coriolis force, the wind has to accelerate to a greater speed. And so you get faster motion, indicated by bigger arrows, where the isobars are closer together. And you have weaker geostrophic winds, where the isobars are farther apart. It's all still geostrophic, it's just that the speed of these geostrophic winds is determined, it's consistent with the geostrophic approximation, to use the right terminology. It's just that the speed of these winds is being determined by how far apart the isobars are, how strong the pressure gradient force is. Pretty darn slick. Now, all of this that I showed you, once you know it, that's actually pretty easy. I can give you a map. You're going to have maps in the lab and so on, where you have contours of pressure. You can figure out, just as long as you draw the winds so that they're parallel to the isobars with low pressure to the left and higher pressure to the right, you're golden. It's going to work great. But that was all aloft, where we could throw friction out of the mix. We didn't have to think about friction at all. What about at the surface? Near the surface of the Earth, where air parcels are going to be dragging across trees, power lines, hills, billboards, all that kind of stuff, friction is going to matter. Friction is not going to be small enough that we can throw it out of the forces that are at work So at the surface, we're going to need to think about the pressure gradient force and the Coriolis force and friction. In fact, I made a little summary table here to show you that. I mean, when we made this list of forces for ALOFT, which I have over here, these red check marks, we only had to check off 2 of them. The rest of them we could say were small, but we don't get to do that for winds near the surface. If we're talking about a cyclone at the surface of the Earth, or we're talking about an anticyclone at the surface of the Earth, there's no way. We can't get rid of friction. Friction is important. It's as important as pressure gradient force and Coriolis force. 3 forces. Oh, well, it's not as bad as 5, but it's still plenty terrible. We still can't take this. I actually just took the old slide and crossed some things out. If I'm going to cross out the word aloft and say, what about at the surface? Or with close to the surface or whatever. We called that geostrophic before, but we can't do that anymore because now we're adding friction to it. This is not going to be quite like the Coriolis, like centrifugal, like geostrophic balance, excuse me. We need a name for this. Weirdly, meteorologists have never come to an agreed upon name for what to call this force balance that happens at the surface. It was originally described by a paper by 2 authors, Goldberg and Mohn, and several books do call it the Goldberg-Mohn balance, so that's hard to say and makes no sense. We're going to call it real winds near the surface. Okay, I think that's actually the terminology your book uses, but I mean that's hardly technical language, right? It just, this is when we're really near the surface. What are the forces acting on the wind? Well, it's easiest to think about this if you compare it to what was going on aloft. So I made 2 little diagrams here, where the top panel is supposed to be showing what winds were like when they were geostrophic, that is to say when we could forget about friction, and the bottom panel is going to be what we have to do when we're near the surface. Hopefully by now the one that's on the top panel is a pretty good friend. We see how there's a pressure gradient force towards low pressure, we see how there's an equal but opposite Coriolis force, and the winds are going to be going parallel to the isobars. What if we said near the surface of the Earth? What if we just started with that and we said, well, how would that change if we added friction? What does friction do? Well, friction slows the air parcel down. And if we slowed the air parcel down, what does that change? Well, for one thing, the Coriolis force. Remember, the Coriolis force, the magnitude of it, is determined by the speed of the wind. So if we slowed the wind down by friction, we've also weakened the Coriolis force. But before, remember, back on over here in geostrophic flow, we were counting on Coriolis force and pressure gradient force being equal and opposite. Well, down here in the bottom panel, we don't get that anymore. The pressure gradient force kind of wins, for lack of a better word. Okay? The pressure gradient force is stronger than the Coriolis force. And as a consequence, our wind, which is the black vector there, is weaker than if it was geostrophic, and it's not really quite parallel to the isobars anymore. Rather, it's still kind of parallel to the isobars, but it's crossing them at about a 30-degree angle or something like that. The pressure gradient force is dragging the air parcel from higher pressure towards lower pressure. The air parcel is actually going to cross isobars rather than go parallel to them from high pressure to low pressure, as it still kind of mostly goes parallel to them. Notice that the Coriolis force still has to be drawn at a 90-degree angle to the motion of the object. Coriolis force is still 90 degrees to the right. It's just that that's no longer equal and opposite to the pressure gradient force. It's almost geostrophic, but not quite. Again, I zoomed in here with my little magnifying glass tool, excuse me, to show you here that the Coriolis force, which is labeled here in green, has to still be drawn at 90-degree angle to the wind. It's just that it isn't equal and opposite to the Coriolis force anymore. I forgot I had this cool slide to show that. Alright, so if I once again drew a big old cyclone in the western United States, and a big old anticyclone in the eastern United States, and I went ahead and I drew all these forces on here, now you're going to take some time and actually pick this all apart, but like at each of these 8 air parcels here, you can see how at each and every one of them, in red, there's a pressure gradient force vector, which is pointing in towards areas of low pressure or out away from areas of high pressure, perpendicular to the contours around them. And then I drew the wind. And I drew the wind to be mostly parallel to the isobars, like it was when it was geostrophic, but it's somewhat crossing the isobars from areas of higher pressure towards areas of lower pressure. Because the pressure gradient force is going to kind of be winning. It's kind of pulling the air parcel in towards the area of low pressure, or kind of pushing the air parcel out away from the area of high pressure. After that, it's just a game of filling everything in. I got to make sure my Coriolis force is 90 degrees to the right of the wind, and I got to make sure my friction is opposite the wind. But I think I have it right on all of these here. This took a long time in PowerPoint, let me tell you, to get these all right. So if you take a look at this, what you see, the resulting winds are just a little different than when they were approximated using geostrophic balance. They still spiral around the area of the cyclone, the area of low pressure. They are going counterclockwise, at least in the northern hemisphere. But instead of just going around the cyclone, parallel to isobars, they actually spiral in towards the center of the cyclone. See how they're actually kind of all directed in. If I could draw this more perfectly, they're spiraling in towards the center. We don't actually use the word spiraling in meteorology. We like the word converge. The cyclone is experiencing convergence. Air is converging in the center. Sounds more technical. Same with on the anticyclone over there in the east. The winds are going around the anticyclone in a in a clockwise manner, in an anticyclonic manner, around that area of high pressure. And they are mostly blowing kind of parallel to the isobars, but they're also spiraling away from the center of the anticyclone. Spiraling away from, we don't like that word spiraling away in meteorology. We like that more technical sounding divergence. There is divergence happening in the center of the anticyclone as the air diverges away. Cool! Cyclones are areas of convergence, at the surface anyway. Anticyclones are areas of divergence. This is going to have everything to do with which one of those tends to have storms and so on. We're just not there yet. Cool. Another thing I want to tell you about these cyclones and anticyclones and real winds at the surface is that just like geostrophic winds, excuse me, just like geostrophic winds, the wind will be stronger the closer together the isobars are. So again here I drew the cyclone and the anticyclone in kind of a goofy way just so that there would be an area where the isobars are close together, that is there's a strong pressure gradient force, and areas where the isobars are farther apart so that we would have a weak pressure gradient force, and I wanted you to see that the winds are much stronger even at the surface when the isobars are closer together. It's a lot like geostrophic balance, this real winds at the surface thing. Okay, before we get a chance to look at some examples of this, let's answer a few questions. Question 12. Why aren't winds at the surface in geostrophic balance? Is it A, because the Coriolis force at the surface is too strong? Is it B, because geostrophic conditions assume that the friction is unimportant, which does not apply there? Or is it C, they are in geostrophic balance? Which of those is the right answer? Make a choice from those three options and get a little feedback before you go on to question 13.